This is the second part of the 4-2 lecture. And in this lecture, we're going to be talking about some good experimental design techniques, and we're going to be talking about some additional design periods of experiments. Um, the logic of the randomized comparative experiment basically saying it's like, hey, I got two similar groups, and they're similar as similar as can be, except for the actual treatment. But the question is, how do we make it so that even the treatments feel almost the same? And that is, sometimes we use a placebo, which is a dummy treatment, and we do this to defeat something called the placebo effect. And the placebo effect is an idea that sometimes people react to even a dummy treatment because of other things. For example, imagine someone who they're testing a diet pill, and some people get the pill, and the other people don't get the pill. Well, the act of getting a pill that even though it doesn't have an active agreement, may make people think about living more healthy lives or eating better or other things like that. And that can lead to a placebo effect. Whenever possible, we should have a placebo. And also, the subject should be double blind. In a double blind experiment, neither the subjects nor those who interact with them and measure the response know what treatment is being given. So everyone's in the dark about what group they're in until you actually see the final results. But in a single blind experiment, only the subjects are unaware what treatment they're getting. Um, let's take this idea and see if we can make some sense out of it. In an interesting experiment, researchers examined the effect of ultrasounds on birth weight. Pregnant women participating in the study were randomly assigned to one of two groups. The first group of women received an ultrasound. The second group did not. When the subjects' babies were born, their birth weights were recorded. The women who received ultrasounds had heavier babies. Did this experiment take the placebo effect into account? And the answer is um, the placebo effect was not taken into effect as there was no, and I'll use the word dummy treatment. There was simply no other treatment. They just simply didn't get the ultrasound. Why is this important? Um, you can think of some mothers, not possessive mothers, some mothers may respond, meaning they have some reaction to the attention. Or there may be something else that they're responding to that the people who did not get the ultrasound didn't get. And it may have nothing to do with the ultrasound. Okay. Thus causing um, a placebo effect. The ultrasound really didn't do anything, but the mothers reacted anyway. Okay. Was the experiment double blind? And the answer to that was the experiment was not double blind. See how I answered the question right away? And then let's say the reason. Because the mothers knew whether they were getting an ultrasound. Why is this important? Again, the reaction to getting any treatment may affect um, birth weights. So we don't know whether the ultrasound is doing it or just any attention that we might be giving. So based on the answers to one and two, can you describe an improved experiment? And I think they mean, can you incorporate both a placebo and double blind? And the answer is um, uh, have a placebo group where subjects get a fake ultrasound. So it's an ultrasound in that they're going into a room. Um, the ultrasound machine is there. It's applied to uh, the mothers, but that is um, the ultrasound machine is not turned on. Now, for that to happen, you can get um, the the subjects certainly are single blind, but the person giving the fake ultrasound, but but you probably can't pull off a double blind. As the person who's applying the fake ultrasound would have to know which treatment group um, get in there. Um, by the way, make sure uh, ultrasound is um, the screen is not visible. That would kind of break the illusion. Okay. All right. So that's how we might make an experiment a little bit better. In truth be told, some experiments simply cannot be done in a double blind fashion. All right. Now let's change the subject a little bit and let's talk about one of the big reasons why we're doing all of this work, and that is to move towards, again, inference. Now, what is inference? We do an experiment and we see difference in responses. Okay. And we want those differences in responses to be so large that they're unlikely to happen by chance variation. It's not that, oh, on this one-time experiment, we saw this little bit of difference, and that little bit of difference is something that could have happened by chance. Think about flipping a coin 100 times and getting 51 heads. Is it exactly what you expected? No, but it's not so outrageously different that you can't think of it not happening by chance. Um, but when we're done, we'd like to be able to apply our findings to a larger group. And that's where we again talk about the idea of inference, sampling, coming to a conclusion, inferring onto a large population. We don't think we can infer onto that large population unless we think the outcome is statistically significant. That is, that the observed effect is so large that it would rarely happen by chance. And we say that a statistically significant association in data from a well-designed experiment does imply causation. we get to the point where we can actually say this thing did cause that other thing. And we call this whole situation statistically significant, which means in class, if we use the word significant, we better be doing it in the context of this particular idea. Experiments well designed and an outcome so large that it didn't happen by chance. Now, in the class notes, we go to this activity that tries to get at the idea of significance. We're going to do this particular activity in class with everyone so we can all get that go through that procedure and see that out. So we're going to skip over the discussion about the activity and we're going to go to this other part of the experimental design possibilities, and this one is called blocking. Um, it talks about this idea that we may have within our subjects or experimental units some commonalities, and those commonalities may have attributes which are known to affect how the treatment is interpreted. So it says a block is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect the response to the treatment. Now, if we know ahead of time that they're going to interpret the treatment differently, the one thing that we want to avoid is to have all of those experimental units that react differently all in the same treatment group. Because then are we measuring how well the treatment affects the groups, or are we measuring the uh, just the inherent difference in the two groups? So what we do to take that into account is that we do what's called a randomized block design, where we have the treatments um, assigned to um, the different treatments assigned within each block. So imagine, for example, we're taking a look at two different keyboard designs for a smartphone. And maybe this is really early in the smartphone era, and not everyone has a smartphone yet. You get 10 volunteers. Well, some of them have smartphones and some of them don't. Well, maybe the people with the smartphones have gotten used to their current keyboard layout and would be not happy about a new layout. And the non-smartphone users, oh, they don't know any different. Well, we think that the new keyboards how they're interpreted may be different within these two blocks. So this step here is called blocking. Okay. And within the smartphone users, now we can do random assignments to our two different treatment groups. Now, within this block, we can do random assignment to the two different treatment groups, and then we can then compare the results. All right. So form blocks based on the most unavoidable sources of variability, lurking variables, and then use randomization to average out all the other lurking variables that may exist. So when we know there's a problem, block on it, and then all the problems that we don't know about, we're just gonna hope that the random assignment evens those out. Let's take a look at a place where a block design may make a lot of sense. It says women and men respond differently to advertising. Researchers would like to design an experiment to compare the effectiveness of three different advertisements for the same product. Probably should be product. Explain why the randomized block design might be preferable to completely randomized design for this experiment. Um, we could say, well, because men and women respond differently to advertisements. We want to avoid having all women in the same treatment group, or all men in the same treatment group. All right. And then our solution, blocking, will keep this from happening. And because the treatment groups can't be as um, won't be as different, we'll actually get a little bit extra benefit. There'll be less variability in our samples. So it's outline a randomized block experiment using 300 volunteers, 180 men, and 120 women as subjects. Describe how you would carry out the random assignment for your design. All right, so let's start with, we have our subjects. And how many of them? There are 300 of them. Now let's block. I think I'm gonna need a little bit more space than that. There we go. All right, oh, lost this. Let's block for our men, where there's 180 of them, and then our women, where there's 120 of them. All right, and again, this step is called blocking. All right, now what do we do? We're going to take the men and break them into 3 separate groups. And this step is called random assignment. And how many go into group 1? And that would be a third of them, which would be 60. How many go into group 2? That will be 60 as well. And how many go into group 3? And that would be 60 as well. And what happens to them? Well, this group sees advertising number 1. This group sees advertisement number 2. And this group sees advertisement number 3. And then when we're done, amongst all the men, we can compare results. And then what happens amongst the women? Again, we break down into 3 groups using random assignment. Into group 1. And that will be a third of 120. So there's going to be 40 in that group. Into group 2, where there's 40 in that group. And group 3, where there's 40 in that group. And then each of these sees the different advertisements. And when we're done, we can compare the results within the women. And when we're done, we can compare the results in general. Okay, that answers that part. It says, how would you carry out the random assignment for your design? Okay, well, um, let's talk about doing the random assignment for the males. For the males, Um, we have to break it into three groups. So I would probably put all names into or onto identical slips of paper, put slips into hat, and of course, mix well. And mix well. Without looking, draw out 60 names. Those are assigned to group one, without looking, draw another 60 names. They are assigned to group two. All remaining names are in group three. Similarly, for women, um, except drawing out 40 names for each group. There we go. And that will give us three randomly assigned treatment groups that, again, amongst the women, all the other lurking variables um, should be then uh, distributed across the different groups. All right, we got one more experimental design, and that's called the matched pair design. Now, in the matched pair design, we have two things, a pair of similar experimental units. Now, the similar experimental units could be twins, because twins, especially if they're identical twins, or they're at least genetically uh, identical to each other. They're very similar. Okay. It could be a plot of land split in half. Okay. But what we're looking for is two things that are nearly identical. Okay. And then let chance determine which of the two in each pair gets which treatment. So you have a pair of twins, one of them's going to get an acne treatment and one of them's going to get a placebo. You've got you got a plot of land that you divide in half. One half of that plot of land is going to get herbicide A, and the other plot of land is going to get herbicide B. And what you end up getting is, again, two things nearly identical, and the only thing that's different between them is the treatment. Now, sometimes the pair can consist of a single unit that receives both treatments. meaning that a single person gets um, acne medicine for a little while, and then they get the placebo acne medicine for a while. And the only thing that then varies by chance is in which order the treatment is given. So people can be their own matched pair, right? Now, one of the things that's important about when we do a match pair design, that um, we are going to not really care what happens with the acne medicine and the placebo. What we care about is the difference between the two. So it says, imagine there's an example where I take your pulse rate when you're standing and when you're sitting, and I want to know, hey, is there a difference? So half of you are assigned to the group in which you stand first, get your pulse taken, then you sit, get your pulse taken. The other group, you sit first, get your pulse taken, then you stand. And in this experiment, imagine this is all the standing pulse rates, and this is all the sitting pulse rates. And fundamentally, it doesn't look like there's a lot of difference there. But we actually don't care about that outcome. What we care about is that we look within each pair of the difference in the outcome. So, for example, for one person, it looks like the difference in their pulse rate from standing to sitting was 21 beats per minute. Okay. There's some people who actually had a lower standing heart rate than sitting, but you can take a look at that and then you ask the question, well, if standing and sitting didn't matter, what would you expect? Well, I would have expected the difference to be zero, but clearly the vast majority of the data points, the difference is bigger than zero. So when we look at matched paired experiments, it's important that we look at the difference in the outcomes in the individual pairs, not the overall uh, uh, results from the separation. All right, so that concludes our 4.2 lecture. We learned about observational studies and experiments. We learned about how to deal with multiple treatments, groups of experimental units. We learned about how to try to control by having multiple treatments. We talked about random assignment of into treatment groups, replication, about making sure that you have lots and lots of experimental units so you can actually see the difference that's really there. That behavioral issues may lead us to want to have double blind, where the subject and those they interact with don't know which of the two treatments are given. We want to make sure that we sometimes have placebos, a fake treatment to keep from dealing with the placebo effect. We also learned out how to block to control for known variations within our experimental units. And we also learned that an experimental design includes matched pairs where you take um, two things that are nearly identical, one of them getting one treatment, one getting the other, and that has its own special ramifications. And that concludes 4.2.